Hey, what's up guys? In this video we are finally talking about how to build an 8x8x8 RGB LED cube. This is going to be part of a series of videos where we talk about the LED cube. But in this video we're going to strictly talk about the theory behind how everything works. So we'll work our way through the circuitry, through the architecture of the cube, how we control 512 LEDs through multiplexing, how we control the brightness of those LEDs via a modulation scheme, and we'll talk about that more later. Everything I show you here is scalable, so you could build a massive cube with 1,000,000 LEDs if you wanted to. I wouldn't use the Arduino microcontroller for that, but we'll talk about how to do that if you wanted to do that. It's definitely scalable downwards, so if you wanted to make this, take what I'm showing you here and scale it down to a 4x4x4, you could definitely do that too. So we'll talk about all that. And my point is though that everything here is very universal, so you can use any microcontroller you want. So you could use an AVR, PIC, the Raspberry Pi, the Arduino, the pickaxe, the propeller, any microcontroller you want. So that's pretty much it. So let's take a closer look and we'll talk about how this cube works. Okay, so let's talk a little bit about the theory here. And I think the most important thing to talk about is really how to control an LED. How do you light up an LED? How do you control the brightness? So let's just start off with a standard LED here. Okay, so you have an LED, and I draw all my LEDs like diodes. And you'll have the current limiting resistor, which is chosen based on the forward current and the forward voltage of the LED in the data sheet. And then you have the pin over here that you would connect to your microcontroller. And when you make this pin go high, the LED turns on. When you make it low, it turns off. To control the brightness of it, you could vary this resistance, but of course that's not possible. So what you do is control it by modulating this pin. And if you hold up that blue board, the Arduino board, you'll notice that some of the pins names will have something called PWM next to them, and that's pulse width modulation. And that's actually built into the hardware of the Arduino, so it makes it really easy to control. And basically what we do here is that pin, you would connect this to one of the PWM outputs of the Arduino, and that pin you write to it by doing something like an analog write. And you can do a value from 0 to 255, and it's 255 because it's 8-bit PWM. That's its resolution. So if you wrote 255, this would be on all the time. If you wrote a 0 to it, it would be off all the time. Okay, so that's its duty cycle. If you wrote a 127 to it, that would be about half of 255, which gives you 50% duty cycle. So you would get like a perfect square wave output of the pin. Okay, meaning you have equal parts on and equal parts off. So your on time here in one period, your on time over your total time is 50%. Okay, that's 0.5. So your duty cycle is 50% right there. It just so happens that the duty cycle is proportional to the brightness of the LED. And when you first see this, you're thinking, we look at this so zoomed in, and you think, how could you turn the LED off? I mean, we would notice that, right? No, it's so fast that you cannot tell that it's actually turning on. It's just sort of, your vision just perceives this as being, you're dimming the LED, okay? So it's kind of cool. And the Arduino PWM outputs are pretty slow, actually. I think they're less than 500 hertz. Okay, I think I'm running my modulation over here in the kilohertz range. I can't remember off the top of my head, but anyway. So that would be like something like 127 written to it. But if you increase that to something like 254, your duty cycle increases and you get a square wave that looks kind of like this at your outputs. Notice how the on time versus the off time is really increased. But that's not how duty cycle is measured. It's actually the on time versus the total time. And that's your duty cycle. Okay, so, that's how it works. But the problem with the Arduino is you only have a couple of those pins available to you, and certainly not enough to control 512 RGB LEDs. And the reason I'm talking about brightness is because we have RGB LEDs. So there's actually 3 LEDs per the package. And we want to mix the colors of the RGB. And the only way to do that is to really control the brightness of each of the LEDs. And we have a diffused lens, so we're actually modulating each of the RGB LEDs. And since the lens is diffused, it sort of mixes all the colors for us, and it makes all the different colors. Okay? So that's that. That's how we control brightness. That's not exactly how we control it over here, but we'll get to that here in a little bit. Now let's take an example of how to control a lot of LEDs. And you usually go back to the grid topology. So if you have a grid here, it's kind of like an XY type of grid, and you have, I'm just going to take a 4x4x4 here. And yeah, it's not exactly how the cube is, but we'll get to all that. So we build up a grid where in the grid, all the intersections are an LED. These are just single color LEDs, not RGBs yet, but these are just single color LEDs. And what we do in the grid, and we want to control 16 LEDs, so we build up this grid, and we tie all of the, we'll call these the anodes, all the anodes together in all the vertical columns, and then we'll tie all the cathodes together in the horizontal rows. And then from this, now we can control any of the LEDs inside the grid via 1, 2, 3, 4 plus 4, 8 pins. It's not really the most efficient thing in the world, but hey, you could control all of this via one 8-bit shift register, okay? Because it's 8 bits, so you get 8 outputs. And we'll talk about shift registers here in a second. So that would mean, again, you'd only need like maybe, 2 pins off your microcontroller, a shift out, a clock data, and a latch. 3 pins off your microcontroller to control 16 LEDs. Anyway, how we control them is very simple. I mean, you make one row low. So make this row, we'll start it off here. Make this row low, and then on the anodes here, you could put your current limiting resistors here. You make this 5 volts. If you want to light this LED up, you make that 5 volts. If you want to make this one light up, you make this 5 volts, this one low, and then you just make these other pins here opposite, so it would be like 5 volts, 0 volts, 5 volts, 5 volts on your cathodes. And then on your anodes, it's the opposite. So if you wanted to light up this LED here, this would then go to 5 volts. These are all still at 0 volts. So you just kind of digital write high, low to light up the different LEDs. So that's how you light up all the LEDs. But in practice, you have to modulate, or not modulate, but it's more of like a multiplexing type of scheme. So each row would have a chance to light up its LEDs. And that's how your control scheme would work. You would let this first row light up for a period of time. Then you turn it off. Let this one light up, turn it off. This one, turn it off. This one, turn it off. So you give each one a chance to light up. And you do that so quickly that, again, these are turning on and off, but you do it so quickly that you can't tell. And you repeat that. So if you wanted to light up, all these LEDs, if this was your pattern you wanted to light up, you would still have to check this row here if anything wanted to light up. If not, you still keep it on for 10 microseconds. So each row gets 10 microseconds to light up its LEDs, and then you move on. So light this one up for 10, turn it off, light this up for 10, turn it off, light this up for 10, turn it off, 10, turn it off, and then go on. So your on time for each of the LEDs would be 10 microseconds, and your off time would be 30 microseconds, right? So the duty cycle here, on time versus total time, is 1 out of 4. So that's on 10 microseconds, off 30 microseconds, or a duty cycle of 1 out of 4. So the best these LEDs here can do is a 25% duty cycle, which isn't too good, really, if you think about it. So one technique they do when you're controlling this many LEDs is they'll lower the current limiting resistor. beyond what is, your typical ratings. You lower it so you're actually pushing more current through. So when it is on for that 10 microseconds, you're slamming them hard, and you're still safe because it's only going to be on for 10 microseconds. Okay, you're only just pulsing it just for 10 microseconds. And if you check the data sheet, you'll actually notice that there is a value in there for max current, and then it's, with proportional some time value. So you can pulse them a little harder. And this is essentially how the cube works. And we'll get into that a little bit more, but I hope this makes sense. And this is how we control things. The reason we can't just like mix and match everything to turn on them all right now is because it's an XY grid. So if, like, say you wanted to turn these on without doing this technique, you would make this one would be at 5 volts. So would this one. And so would this one. Okay. This would be at 0 volts. And so would this one. So you'd have 2 lines at 0 volts and then 3 lines at 5 volts. What this would actually end up doing would be to turn on this one as well. And it would turn on this one and this one. So you would get something goofy like that, which is why we have to go row by row by row and then bring it back around. Okay? Now, this is when things get a little confusing. So we're controlling these LEDs. Each LED right out of the gate, its full-blown brightness is 1 out of 4, 25% duty cycle. And yeah, we could play games with the current limiting resistor. But, be careful with the current limiting resistor here. If you did lower that, what if your code freezes? What if you're stuck at a row? Then that little rule in the data sheet that lets you pulse them a little harder doesn't apply because it'll be there indefinitely. That's when you start having to play games with like functional safety in the circuit, so that if for whatever reason your code hoses up on one row and doesn't go to the next one, then you'll catch that somehow. You could use like a watchdog timer, or you could have it like as soon as my code's done going to the bottom, make a pin go high and then check and make sure that pin goes high with a separate microcontroller or a reset, who knows. So just be aware of that. But anyways, what's interesting here now is you have a 1 out of 4 duty cycle for each row. So the most these LEDs can go is 25%. What if you want to control the brightness? So you're actually controlling the brightness of 25%. To control the brightness, we actually PWM this technique. So we know it goes around 1 out of 4 like this. But what we could do is say our PWM now of the pin to control the brightness, so we want to make it a little dimmer, is not always light it up every time it goes around. So if we wanted to light up this LED at a 50% duty cycle, which means right now it's always on. If it's always going, it's always checking it, and it's always turning it on for its 10 microseconds. Well, to control the brightness of it, what we could do is light it up only half of the time. So light it up the first time, then turn it off, and then light it up, and then turn it off. So its duty cycle, or its brightness, is actually half of the 25% of that you were already at. So that's how you could control the brightness. And that's exactly how we control the RGB LED cube. Of course, we don't use PWM. We use bit angle modulation. Okay, what is bit angle modulation? Let's explain that. So, I hope all that was clear, but PWM is like this. If you wanted to control something for 50% of the time, you get a 50% square wave, something like that. Your carrier frequency here is fixed at some value. Bit angle modulation is a little different. What bit angle modulation does is instead of having this fixed carrier where each one of these nicks here, this goes all the way to 255. Okay? And basically this is a counter running in the background and it counts up all the way. And then as soon as you hit, say this was 127 at 127 with an 8-bit resolution, that would be 50%. As soon as the counter hits 127, boom, it turns the pin off. So that's like standard PWM. That's how it works. bit angle modulation is a little different, where you have to first consider you have your binary numbers here like this, and it goes like your first, darn it, and it counts up something like 1, 2, 4, 8, 16, 32, 128. Okay, I think I got it right. 1, 2, 3, 4, 5, 6, 7. And then I'll get one more in there. 256. Okay, so this is how the value. No, I didn't do that right, did I? 1, 2, 4, 8, 16, 32. Yeah, I did miss one. Like I don't 8-bit resolution doesn't have a 256 in it. 64, 128. Okay, rookie mistake. So anyways, this is 8 bits here, okay? And this is what each value would represent. But what you do with bit angle modulation is you give each value a time. Okay, so let's say 1 is equal to 1 microsecond. 1 microsecond. So if I'm using bit angle modulation and I wrote a 1 to the value that I'm writing, it would only be on for 1 microsecond. It would be on for 1 microsecond. And then you ask yourself, well, what is the off time then? Well, each value holds its value in time. So this would be 2 microseconds. This would be 4 microseconds. This would be 8 microseconds. This would be 16 microseconds, and so on. So your off time, in this case, would be 254. Okay, because the max would be 255. Does that make sense? I hope so. Now you might ask yourself, well, why would you use bit angle modulation over PWM? And in the cube, in this case, the way I did it, it doesn't really make sense at all, because it's supposed to save you CPU overhead, and some say that it kind of smooths out LED brightness. But anyway, I just kind of wanted to try it out. I've never done it before, and it seemed kind of cool. So this is how bit angle modulation works. Each value has its own time representation, so your carrier is not fixed. So if you wanted to write, say, a 5 to it, it would look something like this. You'd be on for, because you have to build up the number. So a 5 would be 1 plus the 4 here, but you would have your little skip here in the 2. So you'd be on for 1, you'd be off for 2, then you'd be on for 4, and then you'd be off the rest of the time. Okay, for you. Okay, until you build up, your 255 there. Okay, and then you repeat that just like you did here, but notice how we sort of have a goofy waveform, and that's how bit angle modulate. And the reason this is so nice is because in this case I showed you have to keep checking it. In this case, hey, if you knew it was 4 microseconds, just let it hang out there. Don't update it until it hits 8 microseconds. So, if you have your free running timer, it kind of makes things simple. In my case, I had to do software modulation. There's no way I could use the Arduino pins, which are nice and easy to use. That's hardware output. Very effective, low CPU overhead. But since I have to do my modulation in a homemade way, this is what I chose. So I have a free running timer that's just continuously counting, and I just check it. So it's like, let me go back here, because hopefully my little grid technique here still makes sense. We still had our 1 out of 4 like that before, but every time I go to check it now, what I'm doing is, instead of having it, so like, let's say I check it every 10 microseconds. So I go back and I update each row. So I move on, and I continue this thing 10 microseconds, and I'm continuously going through. Well, every time it checks, it increments a counter for me. So what I'm doing is, this is actually starting out, in this case, what I would do is make this 4, my minimum time of 4. So the first bit there, so that at least each row could have a 1 in its value for the modulation. So each one would have a chance. So if I wrote this one to a 1, on the first pass, it would light up. Okay? And then we exceed to the 2, you know, and then you would go to the 3, the 4, and then eventually, let's say, because this would become an 8. As soon as the timer becomes an 8, then we're in the off time. So then all those would be off, or this one would be off. Okay, and then eventually here, this would then become, I forget how I did this, but I think that would be 16, because it doubles in binary, 4, 8, 16. So as soon as I got to 16, then I would turn this guy back on. You see what I'm saying here? I hope that makes sense. All right, so let's talk a little bit about shift registers before we go any further, because I have just so many shift registers. I have 25 shift registers, and these are 8-bit shift registers. I think there's 74 HC595, I think is the part number. I'll double check that. But anyway, we're using 4 pins off the shift register, which are the 4 pins of the Arduino, okay, that we're using. We have data, we have a clock, we have a latch, and we have output enable. And I think it's when you make it go low, it turns them on, so it's kind of backwards. But, you know, shift registers are really easy to work with, and I just want to talk a little bit about how to deal with these things, because they sound confusing, and sometimes when you look at the data sheet, it's like, what are they even talking about? So what you do is you have a data line, you have a clock line, and this is how you clock data in, this is how you turn the 8 pins off of the shift register on and off, and how you want it to do. But let's say we have 2 shift registers, okay? 2. The clock line for both of these is a bust signal. It means the same clock goes to both of them. The data line goes into one and then out the other to the input of the second one. And then the latch pin, of course, is a bust signal. And the output enable is also a bust signal. Goes to both of them. Parallel connections. Okay, that's all I wanted to talk about. That was an easy circuit. Point is that the data goes into one and out the other. So let's say I wanted to write, well, let's just write some data to it. So I'm going to make the data pin go high, and here's your clock pin, which will start off as 0. So as my data pin is high, I clock that high, and then I have a 1 that gets clocked in. Okay, and you keep going, and then if you bring your data pin low on the next clock signal, so you're checking it right here and here on the rise of the clock signal, you're clocking this data in, then your next value would be a 0. You see, so you just keep clocking it in, and it's clocking it in. I think you can set this up in the SPI library, and that's what I'm using, this serial peripheral interface to clock this data in. And you could set it up for most significant bit first, least significant bit first, however you want to do it, so that, you know, as it's sending out these 1s and 0s to the output of your shift register, it'll send them out in different orders. And it really doesn't matter, and you can experiment with this, which I recommend doing before you even build a cube up like this. But let's say you get all your data shifted out, and you've got some value here, and it's 8 bits, 2, 3, 4, 5, 6, 7, 8. Okay, so there's your value. Now, if you keep shifting the data, if you just kept going with it, this value here would just go to the next one. Okay, so this ends up being on the last one. And then you have another value that you shift in, and that would be somewhere over here. So you have another 8 bits there. Once you get it all shifted in, you filled up both shift registers, that's 16 bits of data. Okay, each one is a bit. So that's 2 bytes of data. You clocked it all in, data's done. These 2 pins can chill out, they're done. As soon as you latch it, as soon as this latch pin just goes high for a second, this data becomes the outputs of the shift registers. The output enable, if you don't have to do anything with it, you could just keep this high, or did I say high? Keep it low, so you keep that at 0 volts. But what I decided to do was toggle this pin as I'm latching the new data in, because you know you've had a value at the output before this. Now suddenly you changed it quickly. Well, it's going to take time for the LEDs to turn off and on, and you're controlling both sides of that grid. Remember that grid I was just showing you? So these shift registers controlling both of them, and there's delays all over the place with this, and you're getting into a weird realm of physics when you talk about this LED cube, because there's just so much wire and so much data. This clock and data line are clocking at 8 megahertz, so it's pretty fast stuff. So it's so fast that what I decided to do is just toggle this pin right before I latch, and then make it enable everybody right after. So you make the outputs to the new value with the latch pulse. But right before that, we made this pin go high so that all of the outputs actually go low. And then as I latch it, so it's ready to go to the next value. And then right after I latched it, I make this pin go back to a low value, which allows everybody to turn on. Okay, so that's why I used the 4 pins off the Arduino. That's the shift registers. Now we can talk about the cube. So we've got 512 RGBs. That means we have an 8 by 8 by 8. If you looked at the bottom of the cube, it's really just a big 8 by 8 grid. 8 by 8. Which means we have 64 connections downward. And what I decided to do was do it in a pillar sense. So we have 64 of those. So this is each one of the RGB LEDs per pillar, and we have 64 of these. Why do I have this one? It's because I blew this one up in the cube, doing something really stupid. Soldering to an LED, a loose connection, while the cube was powered on. Not a good idea. Blew out the whole row, or blew out the whole pillar, and I had to replace it, and it was not on an outside column. So not easy to do. But I have this as an example to show you how the architecture works. What we have here, you'll notice there's 3 leads at the bottom here. That means we have the R, the G, and the B all connected per pillar. The anodes are connected per each level. So you can't see that lead, but those were all sticking out here. And then the anodes per all the levels, each level, and there's 8 levels, are tied together. Okay, so what that gave us was 64 pillars, and since there's 3 LEDs connected coming down, we actually have, well, 64 times 3, which gives you 192. So there's 192 pins down there, 192 pins coming off of all these ribbon cables down, and those are all of the cathodes. These are common anode LEDs. Okay? So you have 192 cathodes. Let's draw it. You have I'm just going to have it like this for now. RGB. And then you have, that's 8. 1, 2, 3, 4, 5, 6, 7, 8. And then you have anodes up here for the levels. So you have 8 anodes, 64 cathodes per color, gives you 192. So that is the architecture. That is exactly how it's built here. So we have all of the anode levels coming down, and we have 192 cathodes. So what this tells you, and it's the same thing as the 4x4 grid I just talked about, but what this should tell you is that each level is multiplexed. So what I'm doing is turning each level on, and each level has a single chance to turn on. So the duty cycle of every single LED in this cube, the max it could be on for is 1 out of 8. So it's actually worse than that other example. Okay? So it's not too good, but you'd be surprised. You can get some pretty decent brightness out of that. So 1 out of 8. And I didn't really play too many games with the resistance, the current limiting resistor, because I was a little nervous about it freezing at a level and burning out more of these pillars, because they are not easy at all to replace. So that's exactly what we do, and then we use bit angle modulation to control the brightness of each of the LEDs. So it may go all the way up to 8. Okay, so it starts in my bit angle modulation. If I wanted to write a 1 to one of the LEDs, it would have to be within the, the 1 to 8 counter. So it goes 8, and then it would go 16, 32, 64. And I'm not using 8-bit modulation. I'm actually using 4-bit modulation. Okay, so it's actually something like this. So I could write any value I wanted to it. Actually, the most I could write to it is 0 to 15 as a brightness. So just like I was telling you on the Arduino pin, you can do an analog write of 255. In my case, you can only write a value from 0 to 15. So if you wrote a 1 to it, you would be in this column here, so it would be on here for an 8 count, just so you get every single row has a chance to turn it on at least one time. Okay, because it takes me 8 clocks to get all the way up. So if I did write a 1 to one of them, it would only be on for 1 out of the 8 times anyways. And then it jumps right over to the 16, counts all its way up, which would be 2 of the 8s, and then to the 32, which would be 4 of the 8s. Okay, so that's like if I wrote, let me see if I could just explain this a little better. So this is a 1, 2, a 4, and then an 8, and then that gives you your total of 16. So if I wrote a 4 to the brightness of one of our LEDs here, if I just wrote a 4 to it, it would be off for the first roll through, and then it would be off for the next 2 roll throughs, and then it would be on for 4 roll throughs in a row, and then it would be off for the rest, okay, which would be the next 8 roll throughs. Okay, that's bit angle modulation. That's how it works. That's how the LED cube works. Let's talk hardware. All right, so let's take a look at the hardware that's in the cube build here. So there's nothing really too complicated. It's actually just a few transistor circuits, and this is the power control. What controls this circuit is the shift registers, and I'll draw that up here next so that at least you can, if you need to build it and I don't have a schematic for you, you can at least sort of copy what I have here. So basically though, the cube looks really complicated, but it really isn't. It's just the same circuit over and over and over again, because I said we have 192 cathodes coming down, and then we have 8 anodes to control. So we have here is 2 circuits. We have the anode control and we have the cathode control. And I always think it's a good idea to make a pin go high to turn it on. You know, I showed you this is a common anode LED, so technically you ground the cathode to turn the LED on. Well, in this case, I'm actually making a pin go high to turn it on. And this will make sense here in a second. I'm probably getting a little off base here, but so essentially, let's go through the anode control circuit. Okay, remember, we have to put 5 volts on the level, okay, on the anode level for each level. And the duty cycle is 1 out of 8. So we have 8 of these circuits, and it goes level by level by level. So we actually have 8 of these, and our source power is right here, the 5 volts. And let's just work through it. We have a pin connected through a 1K to an NPN BJT type transistor, and these are 2N3904 transistors. I mean, you don't have to use that transistor, just any small signal type transistor like that will work. So its emitter is connected to ground, its collector is connected through a 1K to 5 volts, and that's just the pull up there. And this is the driver circuit to control this thing, which is a P-channel MOSFET. Okay, I decided to use these I guess I didn't really have to, but anyway, I decided to use them. And these are IRF9Z34N. So we have that right here, this point here connected right to the gate. And P-channel MOSFETs are like the opposite of N-channel MOSFETs, obviously. But in order to turn them on, because we want this right here on the source pin, this 5 volts, to end up on the drain pin when we turn it on. But in order to turn it on with a P-channel MOSFET, you actually have to bring the gate pin low. So that's what this transistor does. As soon as I make this pin here high, it saturates this transistor and it moves the state of the gate pin from a high, because it was getting pulled up here, to a low, because this just becomes like a switch and it pulls it low through the emitter. And then it turns the P-channel MOSFET on. We get 5 volts through the source to the drain, out to the anode. And then you're asking yourself, what about this 100 ohm resistor here? That's all that is. This is like a pull down, okay? So it kind of quickly snaps it down when I need to turn this off. Okay, and that's kind of what it does. And also it helps if you're not turning any LEDs on in that level, it helps it turn it off. Okay, so at least it's got some current there. So it kind of keeps things a little snappier. And there's probably some things I could have, done here to make it a little bit better. And probably could have used N-channel MOSFETs too, as a possibility. But right here, this 5 volts here, it sources all of the current for an entire level of LEDs. So which is 192 LEDs. So you need to make sure that these wires here are huge. In fact, I think I ran a few 5 volts through there. You have to run a couple wires through here too to the level. I think I ran like 4, or actually probably more than that. I probably ran like 8 ribbon cable wires because they're so small of a gauge. So anyway, because you're pulling a lot of current through here, and I think we'll get into how much current that is here in a second when I talk about the cathode, because up until this point you don't see any current limiting resistors. So anyways, that's how we source 5 volts out to the levels. So we have 8 of those. Then down here is the cathode control circuit. This is the input pin, so this is where the output of the shift registers goes, drives a 1K to another NPN BJT type transistor, NPN, and this again is a 2N3904. And so we're saturating this transistor here, and then there's a 1K here to pull it up to 5 volts, the collector pin. So when it turns on, it basically pulls this low. And what we're pulling low is right here. This is the cathode. So if you imagine here for a second, here's your LED, there's your anode, here's your cathode. It sinks through the current limiting resistors here to the collector. And when this pin is off, this is being pulled up to 5 volts, not allowing current to flow through the LEDs. So that's its off position. As soon as I turn that pin high, the transistor saturates, pulls the collector low, and then current can flow down through the emitter to ground. So you're completing the circuit with the transistor. So you need 2 things to happen in order to turn the LED on. You need to be on the right level, and the right cathode needs to be turned on. Now I have two resistors here, and these are both 100 ohm resistors, but there's only 2 of them for the green and blue cathodes. The red cathode is actually only 1, because remember I was telling you that the RG and B LEDs within an RGB LED all have different forward voltages and forward currents. So it turns out that if I had it like this for the red LED, it's just too bright and it pulls too much current. So in order to do that, I got rid of the 1 resistor. Okay, so you sort of add all this up, meaning I have 192 of this circuit. So I think in my demo video, I give you a total count of the transistors. There's 192 for the cathode, and then there's 8 for the anode, giving you 200 NPN transistors. And then you could add up all the 1Ks, 2 for the 192, and then plus the 2 for the 8. You sort of add all that up, and you get over 400 or something crazy. So that's pretty much the entire hardware circuitry. You just have to imagine this being repeated a ton of times. Now I was talking a little bit about current. For each one of these outputs here, for one of these, it's lighting up an entire level. This was calculated to be about 30 milliamps. So you take that 30 milliamps times 192, and that's what you need to source through this guy. Okay, which is a ton of current also on your 5-volt supply here. You're really yanking hard on it. So I put some giant caps in here, like I think like a couple hundred microfarads, probably even a few thousand microfarads. So I put in some heavy duty caps right there, just so you have a nice stable supply and you're not really yanking it down too hard. And of course I put 0.01 microfarad capacitors everywhere on this circuit, just to, when I say everywhere, just like on the digitals, on the supplies, not anywhere else on the signals that would throw things off. Okay, so now that's pretty much that circuit, and that's all really I have to talk about. It's that simple. So let me draw up the shift registers. Okay guys, we're at the home stretch here, so just a few more things to go over and then you're ready to build your own LED cube. So we have the Arduino here, and we have the shift registers here. We have 2574HC595 shift registers. We have one for the anode control. So each shift register is 8 bits, meaning it has 8 outputs, 0 through 7, 8 outputs. So we have one for the anode, and then since we have 192 cathodes to control, 64 for each color gets 8 shift registers. 8 times 8 gives you 64. And here's the Arduino over here, and these pins refer to the Arduino pins. So when you look here, you'll see like pin 0 keeps counting all the way up to 13, and that's what I'm showing here. These pins do not correlate to the physical pins. So when you hold the chip up and you count like the shift registers here from the top left around counterclockwise, it's not the same thing. So like TX is actually, if you started at pin 1, TX would actually be pin 2, 3, 4, 5, 6, and then it wraps around to the other side, which I don't know what those are. But anyway, not a big deal. You can easily find out what the pin mapping is if you decide to do a standalone chip like I did here. Okay, so anyways, let's talk a little bit about what we got going on here. So we have the data pin on Arduino pin 11. That goes out to data in of the first shift register, which happens to be the anode control shift register. Okay, so we go in there. Hold on one sec. Okay, just want to make sure I'm recording this. That would suck. So we the way we have them set up is the first anode control shift register. So that's the first one we go to. It goes in, out. Here, see D out is pin 9. D out goes to the D in of the first blue shift register, and it goes through all 8 of those, then to the green, then to the red. And the way you shift the data in, it just keeps pushing it down all the way to the end. So when you write data to this thing, to all these shift registers, you write the red, green, blue anode data. So if you would actually write your anode bits last, because everything gets pushed down. So you write red first. Okay, so that data goes in and out through the whole thing, and then all the other signals are bus signals. So each shift register has its 8 outputs, a ground and a VCC, and this VCC should have a 0.01 microfarad capacitor to ground, just as a bypass cap to sort of keep the supply voltage steady during all this switching. We have the data pin we talked about. The blank pin is the same thing as output enable. So if anytime we pull that pin high, all the outputs go away. They turn off. So that's right off of Arduino pin 4. And you'll notice here I have a 1K pull up to 5 volts off that. And that's just so during boot up, or whatever, during boot up basically is like when we're not sure what we're setting all these pins to, the pins all default to an off state. And then that goes to the blank, and that goes to the blank pin across all 25 shift registers. Okay, latch pin, same thing. All 25 shift registers, it goes off pin 2. And that's pretty much it. We have S clock, which is the data clock. That's off pin 13 here. And that goes to all the shift registers. And then VCC on pin 10, I forget what that is, but tie it to 5 volts. And that's it. So once you get all that going, and you'll start realizing that it's not really too complicated of a circuit. It's just insanely repetitive. So that is the RGB LED cube theory video. Next up will be somewhat of a code walkthrough and then possibly a build video. And then I was kind of thinking, if you have any questions, if you've made it to the end of this video, leave a comment down below on any questions you might have, and maybe I'll make a follow-up video sort of answering all of those questions, because I sort of blasted through this. I got to be honest with you, I just recorded this thing straight through, so I'm kind of burnt out. Probably forgot a lot of things. So leave a comment down below if there's any questions. Otherwise, thanks for watching.